This is Chris Cantalupo. I'm a developer of the GeoPM software package. This video is describing that package's tutorial, in particular tutorial number 1. Please refer to our video on tutorial 0 for an introduction on how to build the tutorials and the basic workings of the scripts. In this tutorial, we show how an application with a variety of regions in it that have different computational properties can be profiled with GeoPM without modifying that application with the GeoPM APIs. So here we are in the Git repository in the tutorial subdirectory. And if we look at the README, we're going to be going over section 1 here, a slightly more realistic application. And this tutorial, we'll look at the main, which is in tutorial1.c. This tutorial, and with the following tutorials, you'll see that we do explicit error checking. And here we start off the application in the same way as tutorial 0. We get the com size and the com rank, and we display that on the screen. And then you'll see that there's a for loop. This loops over 10 iterations. It's set here, the number of iterations. And in each iteration, it does a sequence of steps, starting with this tutorial sleep. Then it runs the function tutorial stream. And then it runs dgem, stream again, and all to all. So we'll look into exactly how these regions are defined in just a moment. But you can see the basic structure of this application is to loop over a sequence of function calls and print out every time through the loop. And then at the end, it just says it's complete and calls MPI finalize. Okay, so we have built all the tutorials. Our directory looks a bit like this, and we're going to be running tutorial1.sh, which looks very much like tutorial0.sh. The only difference really is that the output files are named according to their the tutorial numbering, and we're actually executing tutorial 1. Okay, so we want to set MPI exec so that it will run our application on 5 total ranks per node with this affinitization mask, where we have 16 CPUs assigned to each rank that's running the application. And we have our additional rank for running the GeoPM controller. And this setup we're running on 2 compute nodes. Once we are running these region tutorials, we'll be using the OpenMP runtime. So we have to explicitly set OMP num threads. Excuse me. You have to explicitly set OMP num threads to 16, and that corresponds to how we set our mask, the 2 Fs. And then we're going to call our MPI exec with 10 total ranks across those 2 nodes. Oh, we have to change in the tutorials directory before we run these tutorials. Okay, so this is running the tutorial. We get the output back from Slurm about the affinitization mask. And while that's running, it takes a little over a minute. We'll take a look at what those region functions actually are doing. So if we look in tutorial region.c, the definitions of the functions that are being called are written out. So for the sleep region, it's pretty straightforward. This input parameter, big O, which should be the complexity, is directly translated into seconds, and we call clock nanosleep for that many seconds, and then return. In the dgem routine, again, we have this complexity, big O measure, that's passed in, and we want to do a general matrix multiply that has a complexity measure given by big O. So we use this formula here to determine the matrix size. And because dgem scales is n cubed, we take big O and take the cube root of it, and that gives us basically the matrix size modulo a factor. And that's calculated to give us a runtime that's somewhere near a second, that is within a few orders of magnitude of 1 second. Okay, so once we figure out the complexity measure and how that translates to the parameters for the dgem, we initialize some memory after allocating it. And then we go and execute dgem, which is part of laws. And in this case, since we're using the Intel toolchain, we'll be linking to MKL for the dgem implementation. The memory is then freed, and the function returns. In tutorial stream, we also take a big O complexity measure. This translates directly into the size of the vector that's going to be streamed out of memory. There's some allocation and some initialization of values. And then the streaming section of this code is this equation right here, which is looped over to do a addition of two vectors with one multiplied by a scalar value. Again, there's some cleanup, and then the function returns. Finally, our network-intensive operation, the tutorial all-to-all section, we have a rough estimate for how we translate this complexity measure into the size of the buffers that we're going to send in the all-to-all operation. And that's done here. And note there's an explanation for how that equation was derived, and it's somewhat rough. Okay, and then there's some initialization of the memory. We call MPI all-to-all, call into a barrier, so you'll see that when you see this function, there are two MPI functions associated with it in the accounting, and then we clean up. Okay, so let's see how we did over here now that the run is complete. We can take a look at the reports that came out. If we look at the script that we ran first, we'll see that we output these files here, this report. So if we cat tutorial1 report, and then append the node names, which is Mr. Fusion 1 and Mr. Fusion 2, we'll see our report, and it shows that the overall runtime was about 2 minutes, and the runtime spent in MPI accounted for a small, or about half of a second of it. If we look at the second node that we ran on, we'll see the report looks like this. It's similar, but not exactly the same. There's also a trace that was produced. I won't go into trying to parse that out. It looks very much like the trace from tutorial 0 without really looking into detail at the numbers. Okay, well, that's about it for tutorial 1. Please join us next time for our next video, and in that one, we'll start to add some markup to this tutorial 1 so that we get some per region accounting in the output reports. So tutorial 2, that's here. Tune in for that next time. Thanks for joining.